Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I'm so pleased to have Teng Yu here. Teng Yu currently is a PhD student from Princeton University and the Computer Science Department. His advisor is Sanjeev Arora, and I think it's a well-known name for many people here. Before he got a bachelor degree from Tsinghua University, is also in Computer Science Department. And Teng Yu will stay here for 2 days, today and tomorrow. So if you want to meet him, please let me know.
Okay, yeah, thanks for having me here. And I'm going to talk about analyzing non-convex minimization for sparse coding. And this is the joint work with my advisor, Sanjeev Arora, and Rong, Microsoft Research, New England, and Ankur Moitra from MIT. So sparse coding, which is often also called dictionary learning. I guess sometimes I will use dictionary learning just because I usually use that notation, that terminology. And so the key idea is, so data has, in many settings, data has a sparse representation in a different appropriate chosen basis. So Y is our data. And if you choose appropriately a matrix, A, so each column of A, I use A sub I to denote the ith column of A. And if you try to write this data in this basis, then you will get a sparse vector X. So X is the representation, and by sparse I mean that there are at most, say, k non-zeros, non-zero entries in X. And so just to emphasize, so this dictionary is unknown usually, not as so if the dictionary is known, then this is a sparse recovery or sparse linear regression problem. But here we are interested in a setting when the dictionary is unknown, and it's an n by m matrix, and usually we are interested in the case when this dictionary is overcomplete, so where m is larger than n, but maybe not too much larger. And so when m is larger than n, then the number of the columns of A are not independent. So it's a redundant or overcomplete basis. So because the dictionary is unknown and the representation is also unknown, so this is an unsupervised learning problem. So you have no hope to find A and X if you are just given one Y, right? So we are given multiple samples Y, IID samples from the same distribution. So I'm going to use superscript to index the samples. And so then my data is a matrix, and I'm going to decompose this matrix approximately into two matrices, the product of two matrices. One is a dictionary, and the other one is the representations. So each column of this representation matrix has at most k non-zeros. And sometimes I use capital A, capital X for this X matrix and capital Y for this data matrix, just the notation. And so this problem originated from Oceanson Field, the seminal work of these two computational neuroscientists in 1997. And so they were asking the question, why human visual system can recognize the object very quickly and very robustly. So they try to understand the human visual system. And the idea is just the same picture. So on the left-hand side, so this is the first layer of neurons of our visual system. And so these layers of neurons got activated by the light from outside. So you see a picture, and the neurons got activated. This is just the raw data. And then somehow the first layer, the synapses, usually it is called the primal visual cortex, V1. So then after processed by this visual cortex, then you got a sparse representation. Right? The neurons in the second layer, only a small number of neurons got activated, and it turns out that neuroscientists believe that the number of neurons in the second layer is much larger than the number of neurons in the first layer. So this is an over complete matrix. And And so basically, neuroscientists believe that this is a very reasonable model for the first layer of neural visual system. And so the reason I mentioned this is, one of the reasons is that this is the origin, and the other is actually these two neuroscientists, they also proposed a very good model for this, and also a very good algorithm, which I'm going to talk about. So, and so then computer scientists see this very nice explanation and try to use it for our image problems, because we believe that if human eyes could do it just by neurons, neurons is a very weak computational unit compared to computers, right? So then we could do it. If we could do it on neurons, then we could do it in computer. So then here is exactly the same picture. So we get the image or image patches, and we want to represent our image patches by this sparse in this spaces with the sparse representation. And if you learn such a dictionary and you represent your image patches by sparse representation, then what you can do, you can imagine, if this is a nice representation, then maybe you can do supervised learning using this nice representation set of features, or you can do reconstruction, right? Because this is just the approximation. If you multiply this with the representation you get a slightly different image. And this is a reconstruction. Presumably, this could be better. You could denoise the original image, or in super resolution, I think people use this to restrict the space of the possible images. Because you know that your image has this structure, then you know, okay, not all the images are possible. So also a very important fact is that so you can use these representations to build a higher level of representations, like in deep learning. And actually, in visual system, this is just the second layers of neurons, and we have many other layers behind it. So this is the application of this problem. And so also this the deep learning is one of the motivation. So because we want to understand the deep learning, and it seems that this is the simplest version of deep learning. Not even a version of deep learning. It's just a building block of deep learning, in some sense. So it's a good starting point for theoretical understanding. So this work is. Our aim is to theoretically understand this type of problems, and the heuristics that is used for this type of problems. Okay, so we want to have some not only efficient algorithms, but also provable algorithms. So basically, algorithms with provable guarantees for this problem. And this is my outline. So I'm going to first introduce some existing heuristics that is used in practice, and then some models that allow us to understand this problem from a theoretical point of view. So recall, we want to decompose this data matrix into a product of an over-complete matrix and a sparse matrix. So Oceans and Field, they propose this energy function. So they want to minimize this energy function. So this energy function consists of two terms. One is this reconstruction error. Right? This is just when you fit the model, what is the error? Right? What is the error? And this is the sparse penalty, so which enforces that this X matrix is sparse. So you can, for example, use L0 sparsity or L1 sparsity. The exact form of this penalty is not relevant to this talk, but certainly you can think of that, say, L1 sparsity. And so Oceans and Field propose. So we want to minimize this energy function over A and X, because both A and X are not known. And so these two neuroscientists, they propose this alternating update algorithm. So the algorithm is very simple. So you repeat until convergence, and you alternate between these two steps. The first step is you fix A and update X. And so there are different choices of these steps, but what they propose is just you take the minimizer. Because when you fix A, then this energy function is the sum of the reconstruction error of each sample plus so you can decompose this energy function into different samples. So you can treat each sample separately, and you just take the minimizer, via some approach. So, and for example, if this is L1, then this is convex. So, and then the learning step, so you fix X, and you try to update A. And the way that they propose to update this A is you just take gradient descent. You take the gradient of this energy function with respect to A. Now X is fixed. You only take the gradient, partial gradient with respect to A, and then you choose the learning rate eta, and you update your A to be A minus eta times the gradient. So actually, there are many other algorithms for this problem, and they are basically the efficient algorithm are of this form. Under all fall in the same framework. You have this decoding step and learning step. So the only difference is how do you decode and how do you learn, update A. So let me just do a little bit survey of the existing algorithms. So I think there are three interesting algorithms in literature. One is this Austin field algorithm. I refer to it as neural algorithms. And the other one is this MOD, method of optimal direction. And the third one is this KSVD. So recall that we want to minimize this energy function. And in the decoding step, OF just take this minimizer. And in KSVD and MOD, they use these pursuit algorithms. So recall that in this decoding step, we fix A. We want to minimize over X. And this is essentially just the sparse recovery problem. And you can use different tools. And now L1 minimization is the dominating one, I guess. But before that, there are even simpler algorithms like pursuit algorithm, which is essentially you just so you want to find the sparse vector X here, and you just choose the non-zeros in a very greedy way. So you choose so first you pick some entry which explains your data the most, and then you choose the next until you choose exactly k non-zero entries, and you are done.
Just lasso.
No. This is even lasso is you minimize this L1 minimization. L1. So this is even simpler than lasso. It's a even greedy version of
L0.
Yeah. So you really enforce L0 constraint and yeah.
So lasso can be analyzed. People have known.
Yes.
So,
yeah. So yes.
So the analysis you are talking about, you'll be talking about is mainly on the other step.
Because here we don't really know what. So in lasso we assume that you know A, you are given A, but here A is not known.
So that part is harder.
Yeah. So the trouble is that exactly you don't know A, so you have to approximate A and X alternatively, and so that you get close to the truth. So and in the learning step, so the ORF algorithm just use gradient descent. And MOD use this, you just take the minimizer, because when you fix X, then minimize over A, this is just a quadratic problem. Because this penalty term only depends on X. When you fix X, this is a constant. So, and KSVD, this is a little bit trickier. So I just included just for thorough survey, but you don't really. So the idea is that you fix everything else except the ith column of A and the ith row of X. So, and you just update this too. And then if you fix everything else, then this is just a rank 1 approximation. Although you have still two sets of parameters, but thanks to this rank 1 approximation, although this is not convex, still you can do it because you can use SVD. So, and yeah, but I'm not going to talk about this algorithm in detail, just for survey.
So none of them can be analyzed.
None was not known. So we don't know. We didn't know how to analyze it, and now we can analyze the check mark, the one that I checked. So basically, we can analyze this plus this or this plus this, and in this talk, I'm only going to talk about this and plus this.
Yeah, that's not. MOD here. This is a problem, right? So OF is a solution, one solution for two. So when there is a minimizer, is there any special? You're talking about special package?
No. So basically, yeah.
Problem, right?
So yeah, that's a great question. So the minimizer. So here we are fixing X. Yeah. So this is simpler. So this is a quadratic problem. And indeed, so if you take a lot of
this is the definition of learning step, right? Given X, you want to find A to minimize.
Yes. But sometimes you don't really want to take such a big step. So that's why.
Yeah, hoping to get global optimal if possible.
Yeah. So you don't. Yeah. So we are hoping to get global optimal, but this it turns out that this MOD, at least from a theoretical point of view, the step is too big. So we need to make a little bit conservative step. And actually, at least from what I mean, the experiment I ran, just a very simple experiment, this MOD is not as good as KSVD and OF in some aspect. So
in OF, do they actually do early stopping so that it doesn't go too far? Go back to the next iteration of decoding.
I don't think so. But I mean, I'm not sure about the experimental details. So yeah.
You just do one gradient step.
One step.
Yeah, just one step.
Yeah, exactly. So yeah, that's a good point. So you just take one step and then you update this.
The MOD just fully minimize it. Okay.
I see.
So this is alternating algorithm. So you alternate between this step and this step for many times.
Okay. Yes. Okay. Yeah. So that's a super sort of early stopping, right? Just one step.
Yeah.
So I think if you
If you use MOD, this step may be too
There could be
too large.
Too large. Okay. Okay.
so yeah, I think compared to like deep learning, this step is more or less the step of when you calculate the back propagation, and this step is more or less the learning step when you do the gradient set. But I mean, that's probably this is not a good comparison. But anyway, so we are only going to talk about this and plus this, and the main contribution of this work is that we can analyze this algorithm. We can from some good, reasonable starting point. So, okay. So before talking about the theory part, so let me talk about this generative model, which was also proposed by Oceanson Field, and which makes a lot of sense. So because we need to assume something about our data, otherwise, it's too hard. We want to minimize the non-convex function. It's NP hard, and there's no really hope. So basically, we assume that the data is generated from some ground truth A star, the ground truth dictionary, and it is over complete. And we need to make the assumption that the columns of A are close to orthogonal. They are not too parallel. There are no two columns that are very parallel with each other, and they are kind of isotropic, which means that the spectral norm is not too large. So this is and then we assume that this X star, let's say, is -1, 0, 1, but we could relax this assumption a little bit. Probably a lot. So but for simplicity, I'm assuming that this is just to take three values -1, 0, and 1, and the expectation of X star for each is 0. We also assume that the correlation between Xi star and Xj star are kind of independent. So, also X star is a k-sparse vector. It only takes at most k non-zero entries. And then the generative model is that we are given, say, p samples, and each sample is of this form. It's A star times X star plus noise. And the noise is not too large. I won't talk about how to deal with the noise, because even without the noise, this is a hard problem. But the noise, we can tolerate a certain amount of noise, and okay, I omit the superscript here. Technically, this is y superscript j is equals to A star times X star superscript j for the j sample.
Yeah, but in practice, why do they limit X to be -1, 0, 1? That may not be realistic.
Yeah, that's not realistic. Sure. So
only under that concept they can do analysis.
Or? Oh no. So we can relax this. So basically, what we need is, if it's 0, then it's 0, right? If it's not 0, then it should be bounded away from 0. It shouldn't be too small, like a. So this is a sparse vector with a kind of a gap condition. So every non-zero entry is larger than a constant c, like a half, or a lot less than -1/2.
So I know that. So the argument is that it doesn't really matter what X you have, as long as A is more general. You can synthesize you can generate any kind of one.
Yes.
But on the other hand, in practical problem, if X is not limited by binary or maybe trinary, then the result may not be meaningful.
I mean, we can analyze the case when it is bounded away.
It's
Bounded,
so arbitrary x.
Yeah,
right?
as long as it is bounded away from 0. If it is not.
Okay, I see. Okay.
Yeah. So that's the assumption. But for simplicity, I'm going to assume this for this talk. But so technically, our assumption is that x is a sparse vector in a sense, if xi is non-zero, then it must be either larger than a half, say, or smaller than minus a half.
Is there any restriction on this lower bound on this bounded away?
This should be constant.
As long as there exists a constant.
Exists a constant.
I see. Yeah, so x is between 0, between -1 and 1, or is it?
There's no upper bound. There's no upper bound. It's just a lower bound. It cannot be too small. But of course, there are some. I mean, there are some scaling issues. So let's say x, the main range of x is a constant, between constant and.
Okay.
Yeah.
So what is the amount of correlation that you can allow?
So basically, we can allow, I think, pretty good correlation. So say, so if x is a uniform sparse vector, then the correlation between xi and xj is something like k over dimension square. Yeah, and we can allow something like another constant, say a constant times k over m square. Yeah.
About close to orthogonal, is the definition of a matrix in
incoherence. So yeah, incoherence. I'm going to talk about the details when we use it. Yeah.
So even if there are two coordinates that always come up together, that will mess up the algorithm?
That will mess up it. If they are always the same, if say xi is always equals to xj, then that's really a trouble.
Then that's real trouble.
Yeah.
The algorithm is not going to work, you think? Or the analysis?
For sure, the analysis is not going to work. The algorithm, I think certainly you can find some corner case that, when it is not working, but in practice, I think, if just a small number of pairs have this weird correlation, it should be fine. But we didn't analyze it. Okay, so this model makes sense because, the goal is to recover A star.
So for the PIP samples, you do from X star is P different X stars?
Yeah, different X stars.
Okay.
Yes.
It's not that the noise are.
And the noise also different. Could be those.
Okay.
Yeah.
Okay. I just make sure.
Yeah.
So,
So, but A star is the same.
Yeah, the one you wrote is like same X star. You just generate P from the noise.
Oh no.
Okay.
Yeah. So I think I omit the superscript here and here. So you need to have a superscript like J and J here. Yeah. So this model makes sense because if you think about the energy function, right, without the penalty term, the penalty term is just to enforce sparsity. This is the log likelihood of y given A times x. So when you minimize the energy function, you are trying to find the maximum likelihood. And indeed, you can show that when P is large enough, then the ground truth, A star and all the coefficients, and the representations, this is a minimizer of this energy function. So that's why.
That's not entirely true, right? Because
it's not entirely true.
Okay.
Because, sorry?
Because not all x, if I put in x something which is not k-sparse, it's a 0 likelihood.
Yeah. So
it's only sort of a log likelihood restricted on.
Yes, exactly. Yeah. So I guess this sentence means that I'm considering the sparse penalty. Yeah. Without the sparse penalty, this is the log likelihood. Plus the sparse penalty, I will have it is the minimizer in some sense. And also, you need to choose the penalty in the correct way. But this is just the intuition. We're not going to use
so
it.
The property that's associated with the noise is Gaussian distributed?
Yeah, so we are assuming that this is just a white Gaussian noise.
White Gaussian. Okay.
So I'm trying to not talk too much about noise because even without the noise, if the noise is 0, this is not an easy question.
I believe the noise rate has been very difficult.
Okay, so this is the model. So with this model, then we can talk about some theory work. Okay, so the previous works. So we saw that in practice, non-convex minimization, well, this alternating updates algorithm, this is really, it's really good. It's very efficient. It's very simple, and also it's generic. So you don't really need to worry about what the parameters are. So you just use gradient descent of something, and it's very successful. Up to k is less than square root n. K is the sparsity. Let me remind you, and n is the dimension of the vectors. And So and from a theoretical point of view, okay, we don't know whether whether it can get stuck at local optimas, or we don't even know whether there are local optimas. We are not really sure, actually. Right? So it's not very easy to certify that there is a local optima in sometimes.
So this one doesn't depend on what is the learning rate eta.
It depends on learning rate. Yeah.
Okay.
So
that has to be appropriately chosen.
Yes, to run the algorithm, right? Or to make the algorithm work, right? Yes, yeah, you need to choose that. But usually, if you choose that to be very small, then the smaller the more robust, usually, right? So, but the slower, right? Yeah. So and we don't even know. So I think even just 1 year before, we started to know that if we start from, sorry, I think this is not very. So if we start with a 1 over k closed matrix to A star, so we start with a very, very close so if you are given a very close starting point, like 1 over k close column wise, for each column you are already 1 over k close to the ground truth, then you know that this is guaranteed to converge in L2 norm, in Euclidean distance. Yeah, I'm going to use Euclidean distance throughout the talk. So basically we only know very, very small basis of contraction, theoretically, but empirically this is certainly not. The basis of contraction is certainly much larger. I think. Yeah. So and there are many other there are several existing theoretical work for this problem. I listed them. So I think this line of research started from Spielman, Wang, and Wright, 12, and this is the called best paper, and they use the IOP-based algorithm. It's a convex relaxation for this problem, and they allow Sparse to be case less than square root, which is good, but they cannot allow over complete matrix. So in their case, this matrix A is just a square matrix, and the number of samples is something like n squared. You need this many of samples, and the other three authors, Arora, Gu, and Moitra, they had this combinatorial algorithm for this problem, and also Alex Agural and then Kumar and other authors. So they can prove that if k is slightly less than square root n, then you need n squared times 1 over epsilon number of samples. So epsilon is the accuracy. So in some measure, so you need, if you want to get the epsilon accuracy, you need 1 over epsilon times m squared samples, and it can tolerate over complete dictionary. And the third one, this is more of a theoretical interest. Is not really. So this is Barak et al., Barak, Kellner, and Storrow, and they use Lasserre's sum of squares relaxation. If you are not familiar with this terminology, it doesn't really matter. This is very high order convex relaxation. Probably the most powerful relaxation that we know for now, and they can tolerate even larger sparsity, up to almost linear, and but this for theory this is really good. This sparsity this is really powerful, but for practice this is terrible because the number of samples is exponential in 1 over epsilon. So if you want to say get 0.2 accurate, which is very bad, I guess, for practice, you need m to the say 10. This is
you don't show any result on the rate of convergence. How fast the algorithm is?
Oh, they are not iterative algorithm. They are convex. This is convex relaxation. You write down a convex optimization and you solve it. So this is combinatorial. So there is, and the rate is this. M square. Oh no, this is not really rate. So this is the number of samples. Oh sorry. So I guess the main point here is that this theoretical approaches, the number of samples is too large, and they are really not doing as well as the non-convex approach.
Are these all just guarantee or with high probabilities?
With high probability, yeah, it returns the ground truth. Yes.
So the problem is non-convex to begin with, right?
Yes.
So when you're saying that they formulate the problem to be convex,
yes,
so they can analyze it.
Yes.
So do they address the issue how much error you get by approximating the problem?
Yes, they need to address that. So
not here,
not for this for today, but but in this works they need to address that when you do this convex relation, how much you lose.
What do you mean exactly by overcomplete? You mean m is like
m is larger than n. It's a constant times n.
constant time.
Yes.
Not
much larger. I mean, I think this one could probably this one can tolerate m to be n to the 1.1, for example, something like that.
Okay.
But 1.5 probably. I'm the best guess. But anyway, this is not much larger. But I guess in practice we don't really care about when m is much larger than n. Probably. Okay. So I guess the key point here is that the non-convex approach is really the right way from this. I mean, we are really working hard on this problem from a theoretical point of view using convex relaxation, but we never get the same result. I mean, compared to just a simple non-convex heuristic. So the next question, I guess, the natural axiom to ask is whether we can analyze those non-convex optimization approach. So it seems that this is really the right way to do. Okay, so basically this motivates our work, and we try to answer this question, and this is our main theorem. So we have some condition, k is less than square root n, and m is constant times n, and some assumption a star and x star as we described in the generative model slides. And we need to have this. This is very crucial. So a0 is column-wise 1 over log n close to a star. By this I mean that each column, so if you compute the column-wise distance between a and a star, a0 and a star, this is at most 1 over log n. Oh, by the way, the normalization is that each column of a star has unit norm, so that the forbidden norm is something like m square. Forbidden norm square is like m. So, and what we can show is that with this reasonably okay starting point, then we can show that the OF algorithm, this non-convex approach, with a simple decoding rule, which I didn't describe, but I'm going to describe later, and will return a guess at the s iteration as, and such that this is true. So basically, after s iteration, the error decreases linearly in s, so it's a geometry decay of error. And we have some bias here, which can be removed. So, but for simplicity, I'm going to have it because we are not going to talk about the.
So I would expect the results should have eta, the learning rate into it.
Oh, yeah, if you choose, yeah,
it's not there, right?
yeah, I hide it. Yeah, so so yes, though the learning rate it need to be properly chosen, and if you choose the learning rate.
Yeah, but the error should be a function of eta.
Oh, I have already optimized over the learning rate. So I
assume that this is the best learning rate.
So I have already chosen the best learning rate so that this.
Okay.
Yeah.
Is this also hyperability?
Yeah, this is also hyperability. So everything we are talking about is hyperability. But I'm cheating on that. So yeah. Okay. So and this line is really hurting us, right? Because this is
Yeah. So then how about x as the initialization of x?
So we use this decoding rule to initialize x. Where if you have a star, if you have a a0, then we use this decoding rule to initialize x.
So in that perspective, does the permutation of the columns matter? Like you said, column 1.
Oh yes, yeah. So yeah,
you have
that's
to write the permutation or not?
yeah. I have considered the permutation. So up to permutation and sun flip actually. So if you flip the each column with you multiply -1 on each column, it doesn't really change the problem. So up to permutation and sun flip. So this is column-wise closed. So, okay. So and to complement, so we show a spectral method based algorithm, which returns a0, such a good initialization, and that is column-wise 1 over log n close to a star. So, but I guess this is the main part of this this talk, and I'm going to talk a little bit for this initialization. So just some notes. So because this is geometrical decay of error, it means that I mean if you want to achieve epsilon error, you only need log 1 over epsilon iterations. So and the sample complexity is m times k, and the previous one is m squared. So we improve just at least a factor of m over k, and also the sample complexity depends on 1 over epsilon, but here it depends on log 1 over epsilon. So that's the theoretical improvement. And the runtime is m times n times p. So this is really very good because if you want to evaluate this energy function, you need to multiply n by m matrix with the m by p matrix. So even this multiplication takes you n times m times p if you don't use matrix
That's
multiplication.
per iteration. Right.
Per iteration, but the iteration is log. The number of iteration is log n. So I use this tilde to hide the log factor. Okay, but here I use the log. Okay, anyway, right, so okay, so and the initialization also takes the same number of samples, and the runtime is a bit larger. But we think that's in some sense a little bit quite necessary because we are. I mean, the initialization give you a very good approximation, like 1 over log n. So presumably it should take more time. And also all the numbers here could be improved if you change if you assume a little bit more independence on the x, or if you change some assumptions somewhere. So this is not really the optimal, but just a demonstration. Okay, so I guess so now let's talk about how to analyze this alternating minimization. And my plan is that I'm going to give a new perspective and of this kind of non-convex optimization problem, and then I'm going to describe a general condition for convergence, and then I'm going to apply this general framework to sparse coding and show you how to get the result.
Can you go back to see the
Sure.
hidden variable model?
Okay, sure.
Variable?
Sure.
The generative model that you
Sure.
talked earlier. So what is the hidden? Okay, so x is the hidden variable. No.
Okay, x is the hidden variable. Sorry. So I think technically I should write here why the j's sample is a star times x star j plus noise.
Yeah. So so the hidden variable.
Hidden variable is x star. This is the parameter.
Okay. Okay. Oh, so the generative model only applies to one step, only for the learning part.
No. This is the generative model for the data. This is not about the algorithm.
It's not about the data. So to me, I mean, x and x, both a and x
are not known.
Yeah, so it doesn't make sense to talk about one is parameter and one is the data.
Oh, I see. So.
That's what I'm talking about.
Oh, I see. So.
You normally assume that one is unknown, and one is observable. The hidden variable really denotes the unknown variable. You cannot observe hidden variable. Right?
Yeah, both a and x are not known.
Okay.
And so why I call this parameter, because a star is shared across all the samples. So if I write another, and the x star is an independent stochastic part.
Okay.
It's stochastic. So you draw, independent x for each j.
Okay. So that is that's it.
Yes.
Fine.
So. Okay.
Yeah.
Okay. So new perspective. So what is the old perspective? Right? This was my understanding. 10 months ago, for example. So we are trying to analyze this non-convex function e of a times a comma x. And if you write this, this is the direction of x. This is direction of a. What we are doing is, because we are doing alternating updates, so each time we update either x or a. Right? This is the update. And this is a non-convection, and basically our understanding was just, okay, somehow because because this special update rule, this alternating update rule, somehow we can avoid local optima. I guess that was the best hope. It doesn't make much sense. I agree, exactly. But we didn't know much better, right, than this. Maybe there's even no local optima. That's also possible.
But come on, the no local optima. You cannot come up with a small example in small dimension where you would have these local minima. Brute force search over.
For small dimension.
Yeah, just to show that there exist examples with local minima.
For small dimension, we didn't try, but I think we can. But if you, so I think the question is, but if you increase the number of samples, whether you can find it.
I see.
So I think I can. I think I even found, if I fix the number of samples just to be 5 times the dimension, then I can find the local optimum. But if I increase the number of samples, then it's harder and harder to find the local optimum.
It's easy to construct local optimum because of the symmetry, right? Because of you can use a symmetry argument.
Yeah.
You don't remove some columns.
Yes.
It has to be different, same. Unless they're all the same, or everything in between them are same.
Yeah.
Unless that's the case, then they have to be local.
Yeah. So So I guess what I are saying is that there are a lot of global optimals, because if you permute A and X accordingly, then you get exactly the same solution. So in the whole space, there are a lot of global, a lot of minimizers. So for sure, in the whole space, there are many, at least a saddle point, right? Just mathematically, right? So, but in the regime that we are interested in, right, we can prove over log and close whether there is one. That's the, so in the, right, so maybe there's no local optima in this small ball. So, okay, but anyway, this was our confusion, and so we try to propose something that is slightly better than this.
So this is your conjecture, right?
This is not the conjecture. This was our, this was a confusion, right? We don't really understand why this.
Okay.
It's just a confusion, right? So, just for comparison, because I'm going to say something new, and so recall we are going to analyze this, and in the learning step we are going to use gradient descent, right? So, so if you look at this energy function, this is kind of special, like we discussed. So you have this A that corresponds to a fixed set of parameters, and X corresponds to a stochastic part. It's a random part in some sense. And also this is special because if you fix X, then this function is, in our case, is quadratic. So at least it's convex with respect to A if you fix X. Actually, if you choose this to be a convex function, this is a convex function. So we hope to exploit this specialty of this function so that we can prove something, we can achieve something. So, and the way that we exploit is that we observe that if you plug in x star into this function, x star is our ground truth, the truth, right? Which we don't know, but let's do a thought experiment. Let's just plug in x star. We get a function that only depends on A, and this penalty term becomes a constant, and this is a quadratic function over A. So this is convex, but it is not known. It's a hypothetical. It's a thought experiment. But the observation is that when x is close to x star, the gradient, if you look at this and this, right, the only difference is x and x star, right? The gradient of A when you plug in x and the gradient of A when you plug in x star, they are more or less close. Right? This is just the intuition. And the gradient of A at the point x star is the gradient of this convex function, right? Just by definition. So what we are seeing is that this right term, the one that we are interested in, right here, this guy, it is close to the gradient of the convex function, although this gradient is not known. So that's the point. So then we have a different picture. So we define this unknown convex function, and we show that the gradient that we have is an inexact version of the gradient of this convex function. And if you look at this picture, we know that if you follow this one, this blue one, we are guaranteed to converge to local optimal or to global optimal because this is a convex function. And we are in the space of A, this is convex, and everything is nice.
Yeah, but I thought this is precisely the second line that we talked about earlier.
Yes, exactly. Yeah,
So the problem is that it goes too far. So that's why it's not as good as taking just small step, which is not global optimal. Right? Earlier you have three.
Yes.
And this, the one you just talked about, actually.
Yes, exactly. Yes.
Which is not as good as the first one.
Yes, because you are going too far. Yes, exactly. This MOD method, this take the min method. Yes.
So your point is that you want to show that not going so far is better than going all the way to the bottom.
At least.
Is that the main point? Yeah.
That's at least from so. I'm not going to say it is really better because we don't have really evidence, but intuition. At a high level, I think that's true. But at least from a theoretical point of view, if we want to analyze it, we want to choose the eta to be not too large so that it doesn't give you anything too bad. But anyway, so if you follow this blue arrow, then we are going to converge to global optimal. But what we have, this is red arrow, which is approximation in some sense of the blue arrow. So, and we hope that this approximation doesn't hurt us too much, right? So even with the approximation, we can still do something good. So basically, this is the new perspective of this. So, okay, just to repeat the same thing, we are saying that this is converged to A star, and we hope to show that this implies the one that we have converged to A star. So basically, we are asking, okay, whether we have a theory of, say, biased approximate gradient descent. And another question is probably, because we are anyway estimating delta E star, maybe we can use other approximation. And so a note is that this is different from stochastic gradient descent. Because in stochastic gradient descent, the estimation of in stochastic gradient descent, usually you pick some samples to estimate your gradient, but that estimation is always unbiased. So, but here this estimation could be biased, could be. So we need the biased version of approximate gradient descent, and the answer is yes. We can be a little bit more general, and other approximation of delta also converges, and the answer is yes. So that's why we can analyze this KSVD1, which is something that doesn't involve gradient or anything, but still we can think of it as an approximation of gradient descent and maybe some other variants of the Austrian field algorithm. Okay, so this is the new framework, and then we are going to talk about a little. And so, okay, so then our goal is to build this approximation theory of approximate gradient descent in some sense, and actually we'll propose an even more general condition. So we are thinking about this. So we're interested in this linear update rule, right? This first order update, right? So we have some z. I changed the a to z. So the map is z is a, and g is, you can think of this gradient, right? So just because this is interesting of its own, right? So and this is my first order update, and this is my theorem. So this is my condition. My condition says that if GS is somehow correlated with the desired solution Z star, if the inner product of GS between ZS minus Z star is somehow not too small. I guess this doesn't make too much sense at this point, but I'm going to have a picture in the next slide. Oh, just here. So what we are saying is that, okay, this is the gradient of, this is GS, the direction of update. And this is ZS minus Z star. So what we are really saying is just this right arrow, the angle between this right and green one is less than 90 degrees, strictly less than 90 degrees. And the reason why we have this 2 norm here is just we don't want.
I mean, less than 90 degrees, that's not always. Is it always? Is less than?
So this is our condition. If it is always true, then we are good, right?
I see. Okay, so that would require that your gradient is not too far from the real true gradient. If you go in opposite direction, the whole thing will go on.
Yes.
This is your true solution, the desired solution. So you like essentially that condition says that the estimate of the gradient cannot be too noisy.
Not exactly, but I think you get the main point. So basically, if my direction is close to the true gradient, then certainly this is less than 90 degrees.
Yeah.
But on the reverse side, it's not necessarily true.
So you can tolerate some noise, but not too far.
But it's possible that, for example, this is the gradient, the true gradient, and this right direction is my update rule. Both of them are correlated with the desired direction, but they too are not really correlated. That's also possible, but we don't really have an example. But theoretically, it's possible.
Yeah.
So yeah, I'm going to have a picture, I think, in several slides. So, but basically, we are saying that it's not too far from the true gradient. And the theorem is that if this GS always satisfies this condition, so this is something we need to check. But let's say if it is always satisfies this condition, then we have geometrically decurve error. Here the learning rate is here, but we need to choose it to be small so that I think we need the learning rate to be less than 2 beta. So we cannot really choose it to be very large. And we also have some systematic error here. I didn't talk about this epsilon s, but it's some systematic error which we are going to allow because for this problem we really have this error.
So, by the way, for this analysis, does it shed some light as to whether if you allow yourself to go more than one step, maybe a few steps, is it going to do better.
You mean like a accelerated gradient descent? Oh,
No,
sorry.
it's a gradient descent. More than just one step, you can do gradient descent.
Oh, yeah. So here we have S step, right? After S step, we have the error is decay. I mean, it drops to.
Okay, so you have that one.
Yes.
So
It's not only about.
speed up like that.
Oh, I see.
Almost very close.
Okay, so we have. Okay.
So we serve the room at
It's
3:30 or
7
something?
minutes.
Okay, so sure, yeah, I think so. Yeah, yeah. So let's. Okay, so. Okay, so the proof for this is just you can prove by picture. So we are trying to say. So we are trying to show that after S iteration, this error drops with this rate. So then we only need to show that for each iteration it drops with a constant factor. I mean, I omit the systematic error there, but let's say the error, this epsilon are all 0. So we don't need to show this, but this is almost kind of proved by picture, because if this is less than 90 degree and we choose this eta to be a little bit small, then certainly this blue arrow is less than the green one, right? So, and that's it. So, and just a little bit discussion about this. So, there's no objective function involved in this framework. So there's no gradient, no convexity really involved. So we only need some first order update, some update rule, and we have a condition and we can check it. And but actually behind it, this captures analysis of convex optimization, and also this is extracted from the analysis of convex optimization. This is just the most basic thing that people did in convex optimization, and the only thing different is that this is a different level of abstraction. That's the only thing. And yes, okay. So, but we hope that this different level of abstraction can make it more general. I mean, even you can apply it to non-convex problem. That's the point. Okay. So now I'm going to try to apply this framework to energy minimization. And recall that.
But just one point back to your red level abstraction. Yeah, I think. But this has to work locally when it is strongly convex.
Yes, yes, exactly. Yes.
So that's bottom line.
Yes, that's the limitation.
Yeah,
Sure.
that's the limit. That's
Yeah,
why.
That's
why I'm now kind of.
So
Agree with your last point, saying possibly working on non-convex function, because you see, I said the same.
Yes.
Same. We will ask for the analysis essentially the same. It's
So
a
what
different
does
level
mean?
of abstraction.
So
Yes.
what does it mean by right level of abstraction? Yeah.
So just in terms of analysis, this is not so previously we are saying that okay, G must be a gradient of a convex function, and this is my other rule. I'm using gradient descent, and this condition is hidden in the proof. Okay, so previously my theorem is that G is the gradient of some convex function, and then I have this. And now I'm saying that okay, G doesn't have to be gradient of anything; it's just something. And if I have this condition, I have this.
So it's like the vector field of Nemirovsky.
Yeah.
Okay, so putting my point another way is that you, for example, under the alpha strongly convex beta smooth, you can imply these conditions.
Yes. Yes. Yeah.
But
yes.
on the other side, I doubt if you can find some function which satisfies this but do not satisfy strong convexity.
This is, I mean, there's no function involved, right? So that's why it's slightly more powerful, right?
Yeah. But I think if you restrict any function, then that has
Yes.
that's
Yeah. If you reduce to a function, right? That's
Yeah.
But here we are going to apply this to an unknown convex function,
Yeah.
so that's the difference. Okay. So I think, oops, why this doesn't? Oh, here. Okay. So I guess I need to speed up a little bit, but okay. So I'm going to apply this to energy minimization problem, right? So let's see. I think this relates to your question. So how do you use this, right? So I have this alternating update, right? And my decoder is something like this. I'm going to hide it. This is a decoding, and this is the learning. And on the other hand, my framework is that if my update is like this, and I need to check this condition. And so basically, I need to relate this with that. So I mean, I just define G to be this gradient, and with X to be the decoder of Y and A, and I write A is of this form, right? I want to match this too, and this is A is updated to A minus eta G, and basically we want to check G satisfies this. Yes.
And so
Just-
is it true?
Yeah, it is true.
Nice.
Yeah. I mean, locally, only locally.
Okay, up with the
With the initialization, 1 over log and close.
Okay.
But-
perhaps it is in the okay. Yeah.
But we believe that, I mean, 1 over log shouldn't be the truth, right? I mean, it should be something like constant, but
yeah.
But there is no hope that it would be true.
globally. It should be different, yeah. So I think let me escape this probably. Okay, so this is the picture that, so it's possible that your gradient is in this direction, but the one that you have is in this direction. And the angle between the purple one and the red one is very large, but they are both correlated with the green one. That's possible, but that's just artificial.
Purple is okay, right? It's also 90 degree, less than 90 degree.
Yes,
Purple,
so
the green one.
yes,
So the same.
so this is a good thing, right? So
same picture will show the same thing, right?
yes,
So, it
so
doesn't really matter
but
which direction you go.
so the point is just you don't really need to compare the right with the purple. You only need to compare the right with the green.
Yeah.
Okay, and actually, what as you suggest, I mean,
Okay, extra comment. That can be true for the particular instant, but if you want to do a stochastic analysis, then the expectation always between 90 degrees. That's what I would guess.
oh, this is not the unbiased estimate of this, and maybe this is something else, right? You can choose something like something else that that have anything to do with the gradient.
It's just from the picture. If eta is very large, the
Okay.
condition.
It's not going to true, right? Yeah, I'm going to choose it to be small.
Yeah.
And just a very quick, so as you suggested, if you compare if you compare the gradient with this red one with the purple one, that's a slightly stronger condition. And this is exactly the condition in this Balas, Karishman, and Wainwright and Yu paper. And I mean, we realized that this is independent work, and they are doing this on EM algorithm. So it's a different thing, but it's exactly the same type. Right, so EM algorithm, you have the parameter and hidden variable, but although the only difference is when you estimate hidden variable, you don't do a decoding, you do a posterior estimation, and but this is exactly the same thing. So and their condition is slightly stronger. They compare the right one with the purple one, but not the right one with the blue one. So so in their case, this is small. This is okay. So I'm going to I think. Time-wise, it should be fine. Yeah. Okay. So now I'm going to check this condition, right? The last line, right? This is what I need to do. G is correlated with A minus A star. And what is G? That's the. Okay. I'm going to check this. Sorry. Yeah. So what is G? So if you take the gradient, G is this. It's something like this. And let's consider population version. We say let's have infinite number of samples. So let's consider expectation of it. So the sample complexity, I'm not going to talk about it. That's very tough. But anyway, so and X is defined to be the decoding of Y of A. And this is a quite nasty thing, right? Because X is a function of Y and A, and I mean it could be something like our Y minimization, right? You don't really know. So so the question is whether you can have a good form for G so that you can check your condition. And so then the question is what decoding you want to use so that you can really have an analytic form of G.
What is the expectation with respect?
Excuse me?
What is the expectation with respect to?
So if you plug in X star here, right? Is that your question?
Yeah.
Yes, if you plug in the X star, this is just A minus A star. Because this is a convex function. So this is a quadratic function. Yeah. So, but certainly X is not really X star, right? So, and interlude. So what decoding step we are going to use? So let's say our problem is we have Y equals to A star X star, and we want to decode X from Y and the noisy version of A star. And let's say if we are given A star, this reduces to sparse recovery problem, and when we can use this. In this situation, we can use this projection decoding. The idea is that we just take A star transpose Y, and we do a threshold. By threshold, I mean that if this entry is larger than a half, this AI, the inner product between AI star and Y, which is just the ith entry of this A star transpose Y, is larger than a half, then I take it. Otherwise, I zero it out.
Yes, so what do you come up with this projection decoding?
Why did I come?
Because the original problem given A is a convex problem. You do
Yes.
a global solution.
Yes.
But
Yeah.
the point
But
is
that's-
not to go too far.
No, the point is that I need a, first of all, I don't really need that precise solution. I'm okay with the approximation. That's one of the key points. Also, for theoretical work, for theoretical analysis, I want something closed form that has a closed form. If it's a minimizer of a convex function, there's no hope to analyze it. And actually, I think we have some evidence that is not, that is okay. It's comparative, but probably slightly worse than this. So you don't really need to.
So the way you take this ratio, this is just arbitrary function. Is it? How do you make sense of this kind of solution?
Okay, yeah, I'm going to talk about it. Right, so the proof is that, there is a theorem. This dates back to probably 20 years ago. So if A is incoherent, which means that the AI uninorm column and the inner product between columns is less than 1 over square root n, and then if you use this threshold, then the support of x is equals to the support of the true x. So, and the proof.
So is it intuitive that that threshold is sensible as a solution, approximate solution to
I hope I can convince you that.
obvious, right?
Let me show the proof, which is just one line. I hope that I can convince you, but it's not that easy to see. So if you take I star y, this is, if you do the calculation, this is xi plus something. And this sum over j is not. So because x is a sparse vector, so there is only k non-zero entries here. And each inner product is less than 1 over square root n, so this is less than k over square root n. So which means that this A, so basically if you look at the beginning and the end, it says that if you take the inner product between AI star and y, this is xi plus minus a half, plus minus some error, not really a half, plus minus something smaller than a half. So then if you take the threshold and you assume that xi is really is 0, 1, or 0 or something larger than 1, then this threshold makes sense. Okay, and then the next, let's just show that if you have A that is approximately close to A star, and then if you use the same thing, just with A, not A star, you will get the same thing. It's still, and how close you need to be? You need to be 1 over square root log n close. This is exactly where we use this 1 over square root starting point. So we need the decoding to be not correct, but correct for support. So, and actually we can relax it a little bit if the support is not exactly correct, just correct with high probability or with constant probability, probably is fine, but that's a little bit hard to calculate. And so the point is here. So if the support is correct, then I can write this decoding, this threshold decoding, as x is equal to A transpose y restrict to the support. And this is a closed form for analysis. This is and also this is very fast, right? You just take the matrix multiplication. And then I can do this calculation. So I'm going to calculate its expectation, and my decoding is just a closed form, AS transpose y. And I plug in multiple definitions. I'm going to skip this. I guess this just show how nasty this could get. And I plug in a lot of things. Just to do the calculation, I plug in this definition of x into this. And you also need to plug in the definition of y and everything. And take the expectation and a lot of calculation, and we get this. So we cannot get a good form for G, but we can get a good form for each column of G. Each column of G is of this form. It's the lambda squared times AI, minus lambda times AI star times some error. Let's forget about the error, but so this lambda is something close to 1. So this is really correlated with the direction AI minus AI star with some different constant, right? Slightly different constant. And this constant actually converges to 1. So it's really a little bit hard to believe this, but I guess the reason, as you asked, is that if plug in x to be x star, then this is really AI minus AI star. So what we are doing is that it's just saying that if x is not x star, then this doesn't cause too much error due to the cancellation. This cancellation is really important because so basically we are saying that x minus x star, this is something, right? This for individual x, this might be very large, but x minus x star, it points to different directions for different x. So you have this cancellation. Somehow you have this cancellation phenomenon, so that the error is not that much. And here we use the fact that A and A star are both close to isotropic. So the important thing is that we also use A is close to orthotropic, which we cannot really guarantee, right? Because, I mean, A is our estimate. A star is the ground truth. We can assume that that is close to orthotropic. But how do you maintain A to be isotropic? And okay, so I will talk about that in 2 slides. And so then let's check this condition, right? I want to check that G is correlated with A minus A star. And we have this, and this just, we can show this by picture. So basically lambda is AI star. So basically lambda is the size of this. It's the projection of AI to AI star to AI. Right? This is lambda. And here I get lambda square AI. So let me extract 1 lambda from this two term. So this is just so if I multiply lambda with AI, I get this vector. And minus AI star, I get this vector. So, I mean, I guess I'm doing it a little bit quickly, but anyway, it's just you can just show it by picture. And because lambda is close to 1, this is really correlated with AI minus AI star. So for each column, this is correlated, and then we can show it for. We can take a sum and we show it for the whole matrix. So we check this is true. And then we can apply the framework and we're done. So the only thing that remains is that it's caveat. So how do you maintain each estimate to be isotropic, close to isotropic? So the solution one is that each step you can project to the low spectrum norm ball. So that it becomes small. The spectrum norm is smaller. So this low spectrum norm is convex. But so that's a shortcut. And there are some other caveat that I'm not going to talk about, but this is the key idea. And I think I like the solution 2 more, which is that I can use a different G prime, which is y minus ax. So previously we used x here, but now I use the sign of x. So somehow if you use the sign of x, it reduces the noise. So and for this G prime, first I can show it still satisfies this condition. It's still correlated with the desired direction, AI minus AI star. And also, if you use this update rule, then you can just prove, just prove it. You can prove this AI is always less than 3 times A star, the spectrum of A star. So because you use a different update rule. So because this update rule is simpler and it's more robust, so you can prove something stronger.
So does it make sense to do the sign of the gradient itself, putting the sign out of the expectation? That's something very, very popular in, it's called a residuum backpropagation effect.
I see. The sign of gradient. For this case, I think it doesn't. But actually, yeah, I think we can talk offline on this. But this sign corresponds to. I mean, we're inspired a little bit by backpropagation. So, but let's talk it offline if you want. Yeah. So the point is, this G prime is really not any gradient of any function. So that's why that's the power. I mean, that's the benefit of our framework. So we don't really depend on the fact that G is close to some gradient of some true thing. So our definition, our framework doesn't involve the gradient, the convexity.
So why is it better than the original one?
I mean, in practice, this is not better than the original one. It's almost the same, but just for analysis, it's slightly better. It's easier.
Because it's not as accurate. The gradient is not as accurate.
Yeah, but I guess the whole point here is that the gradient is. I mean, it doesn't have to be accurate. You need it to be more unbiased. That's the.
But it may actually turn out to be greater than 90 degrees if you do something like this, right?
Sorry?
The gradient has to be within 90 degrees towards the green line.
Yeah. Yes.
But if you do this, you may not actually have that happen.
Oh, we can prove that it's still.
You would do that?
Yeah,
Okay.
it's still true. Yeah.
Okay.
Yeah. Okay, but this is just some caveat that we don't really care. So let me do this summary. So we show that locally minimizing this non-convex function is close to. You can think of it as minimizing this unknown convex function with an inexact oracle, in some sense, right? And this is our condition. We have this first order update. I mean, this update rule and the general update rule, and we have this condition. If GS is correlated with ZS minus Z star, it implies that ZS converges to Z star, and we can apply this to sparse coding. Yeah. And we need to have some trick for the decoding and things so that we can calculate this expectation. Okay, so the initialization, I think, let me leave some time for let's see. So can I just okay, maybe let me show you this this slide, just this slide. So this is so we want to have an initialization, and what we do, we just pick two samples, U and V, and we compute this matrix Y transpose. This is the two moment, but we weight it by the unit product between U and Y and V and Y. It's a weighted two moments. And then we take the top eigenvector. That's it. So the algorithm is very simple. I mean, so if you don't have this weighted moment, this Y transpose is like identity. So it doesn't make, it's not useful. So the point is that if this sample U, a sample is of form A star times the sparse vector. So U is A star times alpha and V is A star times beta. And take the support of alpha and beta. Let's take the intersection of the support of alpha and beta. If by some chance their support only intersect at one place, then I can say this MUV, this is really, the top eigenvector is really this direction, this T, AT star transpose, plus some noise. This noise is small. So if you happen to choose UV that satisfies this, then you find some direction that is good. This alpha is 1 over log n, something like that. So yeah, I think yeah. So let me skip the rest of. Okay. So and the chance that you find such this thing happens is not too small. It's m over k squared by birth-state paradox. So you really have some chance to find such phenomenon. Okay. So let me skip the rest of this and jump to the discussion and open questions. So the first open question is whether this is generalizable to alternating updates, like EM algorithm, for example, and for other hidden. Okay, I shouldn't. For other hidden variable models, for example, especially EM, and the Wainwright et al.'s paper, right? They study EM, and at least for the problem that they are studying, right, our framework, because our condition is weaker, so it still applies there. But there are two questions that prevents this to be more powerful. The first one is the decoding doesn't have a simple closed form. So this is a technical barrier. So if you don't have a closed form decoding, then you don't know how to calculate the direction of update. So just because technically you don't know how to calculate it. And the second one I think is more essential, and which relates to Xiao's question, and is if this unknown convex function that this E star, if this is not strongly convex and smooth, if this is a smooth function, smooth convex function, then what happens? So then this not, I think I even read some paper by Nestorov, which shows that in this case, I mean, if you have an inexact oracle of the gradient, then the error accumulates. So, but this is not necessary because you can, you can think of, you can change the algorithm or you can find some other ways to avoid it. But they only study the naive way. Probably. I didn't read the paper very carefully, but anyway, in this, our limitation is just our approach. The limitation is it must be strongly convex smooth, and we don't know how to go beyond that. And also another limitation is that this is limited to local convergence, and the local convergence in the sense that it's not really. It's not really need to be a small basin of contradiction. But the limitation is that our framework can only apply to the regime that geometrical decay of error really happens. So for example, for this sparse coding problem, if you initialize with random initialization, you randomly initialize this matrix A with a small trick, then you know that it converges globally. But at the beginning, the reason of the convergence, I think, is essentially different. So it's not really a technical problem. It's just it's essentially different condition, and we don't really understand it. I think it is related to some dynamic system problem, but yeah, I only have some. And also, this may need for global convergence, you need ad hoc analysis because I mean, for some problem, the global convergence is not true. Right? For Gaussian mixture model, it's not true. But for some model, it is true. So maybe we need to really explore the structure of the problem. So in general, here, our framework is not really very sensitive to the structure of a problem, as long as the unknown convex function is strongly convex and smooth. And finally, any practical algorithm go beyond k over square root 10. So we talk about the strong theoretical work, this sum of squares relaxation algorithm, which can go beyond this, but the running time is n to the say 20, which is really not very practical. And this is the. And finally, I guess because Deng is here, so I add these slides about so how can we go beyond sparse coding? This is the main motivation of studying sparse coding, because we want to go beyond sparse coding if you understand it. So one thing is that the simple decoding rule is enough for learning. Right? You don't really need to take lasso or L1 minimization. You can just use a simple heuristic, in some sense heuristic decoding. It's enough for learning. And also this simple decoding rule is really nice. It matches the feed-forward calculation in deep learning. So this is, for example, this is all observable, the image. And if you do the feed-forward calculation, this is something like A transpose Y, not threshold, but some nonlinear function. But rectifier linear, right, they are all similar in some sense. So this is decoding rule is really feed-forward calculation. And the generative model, in this case, in dictionary learning, this is linear generative model, which is not going to be the case in deep learning, because in deep learning, if you have multiple layers, right? The point of deep learning is you want to stack this in multiple layers. And if you have this generative model, you have another layer and generate and generate, right? And linear plus linear is still linear, right? So in the generative model, I think a reasonable generative model for deep learning is y is equals to some nonlinear function of a star x star. So you can stack it. And so you want to stack the layers, and also, so we hope that even if our data is r of some nonlinear function, like say rectifier linear function of a star x star, we can still learn it. But currently we don't know how to do it. But this is I think a nice open question. So if we can learn this, then we can hope to have some provable algorithm for unsupervised learning.
Did you read the paper that I wrote on deep stacking network, where you actually can formulate each step to be convex, but I don't know how to prove it. Eventually, I'll show you.
Oh, okay, yeah.
Layers,
I would love
to combine them.
Okay.
Such a way that you don't have to back application. You can just combine them.
Oh, I see.
I'll show you.
Yeah, I would love to talk about it. Yeah. So and finally, we hope that our framework could use to analyze backprop, in some sense. And we have some preliminary idea for. I think we have some proof for 2 layers under some model, but it's not very. We want to make it stronger. That's the. Yeah. So I guess. Yeah, I'm going to end here.
You are going to change backprop in such a way that you're not going to do just analysis of the original backprop.
Yeah, we might need to change it a little bit.
Modify them a little bit, and then so you get some problem to see whether when you apply that.
Yes.
Revise the version, you can do better.
Yes.
Than the kernel. I think that will
Yeah.
give you some value.
Yeah. Yeah. So okay, I'll stop here. Thank you.
I have a question. Yeah, sure. Yeah, so right now the analysis is based on that the data is generated according to the ground truth model, that's linear. So what would be the major technical barrier if you consider a case with model mismatch? Like the actual data is generated by some distribution, but you don't know about it according to, like with some regularity conditions, and then you still use sparse coding to do the data representation and the modeling. So in this case, and what would be the major technical barrier to generalize the current analysis toward this case? Like which part is the major part that your analysis relies on this ground truth model being consistent with each other?
I think that's a totally different problem.
Yeah. So, I mean, I think, yeah, all of our techniques depend on.
It's misspecified how to. Even the criterion is different. So what would be a criterion to measure is good or bad?
I have a related comment. Basically, so your model, you said you relied on a model, A star, generated data. That has actually have something to do with your condition is your gradient correlated to the direction to the grid to the Z star. Okay, that you can say is an advantage. So you do not need a true gradient, but that's also a disadvantage that you have to get your generative model Z star. Alternatively, a classical position is you will show that the correlation between your function and the true gradient. Now you do not need to know where the true optimal point. Only need the true gradient.
Yes.
If you do that, then you do not need the notion of a true model there.
Yes.
And the similar analysis will also go through. Of course, there the convergence will be seen. This thing will just converge to the local optimum.
This is the best model to. This is the best parameter to use my current model to fit this data. This is actually my.
Yeah. I agree. So, but I would guess that's a much harder problem because you don't even know what is your minimizer, right? In your case, right? So your minimizer is something there. It's not. So and you don't know how to relate your minimizer with everything like data, right? So
there you can
technically,
you can separate in two, right? One is you show you always converges. The second one, the only thing you need to show, I guess I should be the same because second one you already has to be there. The second condition has to hold. Anyways, locally you are strongly convex, right? That means locally you have some point strong point. So the advantage of what I mentioned is that you need to assume nothing about your true optimal point.
This is perhaps a different issue because you're talking about this from the opposition point of view.
No.
But from machine learning side, if your model is misspecified, if I don't know what it will learn.
It would be better, right? You have to regularize them anyway.
No, but the actual machine learning problem is we always have model mismatch, right? Because the point of having machine learning is usually we don't know the ground truth. That's why we use deep learning models or this and that to fit. So basically, we are assuming that probably our model can, in the optimal point, our model could be somehow closely related to the actual data. And then in that case, of course, like for example, with slight model mismatch or something like that.
So actually, even in machine learning and the statistical analysis, then there are two different kinds of Johnson bounds. One is about minimax risk, it's just like here, and the other is about minimax regret. That's about if your model is misspecified and totally different.
So by the way, to follow up that discussion, can you show me your slide where the analysis requires the generative model?
Oh, it requires the generative model everywhere. It's almost everywhere.
So when you say that you actually do have the correct, for example, so maybe this.
I think we require the generative model.
I think that's
so for example, right? So what is Z star? What is Z star? Z star is AI star, right? This is defined by.
If you do have the true gradient, you don't need to have that generative model. So I couldn't follow Xiao's comment on that.
No, I'm just.
So you said that the analysis still can go through.
What I'm saying is that so what I said is just I think it should be roughly equivalent condition, but with different assumptions. Instead of requiring the true optimal point, you can require on the derivation from the grid.
Yeah, it's possible. Yeah.
So that's just two different.
But you don't have to assume that it's a generative model. You should assume that there is a unique solution for the global optimal solution for that.
Yeah, I completely agree. Yeah, that would be better. Yes, but
that's my question. And this is a difficult problem.
But I think this is difficult in a theoretical point of view. Probably. Yeah. Anyway, we will not bother about that for a little.
So that's the point. If you assume locally, you have locally optimal. Okay, locally strong you have a global somewhere there. There. Then the proof technique, if you want to say about convergence, there is to say, like your subdirection is always derived from a true gradient by something. Then you will automatically get that kind of answer. So that's kind of different assumption.
And also, can you also show me where do you use the assumption of the generative model where x is -1, 0, 1?
Oh, we only use it in the decoding.
Oh, I missed that. Which one? Which part?
Here. So we want to prove this.
Okay.
And this assumes that xi not 0, -1, 0, 1. We assume that x is either larger than 1 or smaller than -1 or 0. That's the only thing we need.
I see. Okay. Okay. But you said that it can be generalized without that kind of limit.
So anyway, we need something like this. So we need a condition like xi is either 0 or say, let's say between a and b some constant, and all between -a and -b and -a.
Oh, I see. Okay.
So this is what we need.
Okay. So that if you use that, this was a generalized a little bit. Okay.
So,
Makes sense.
do you have time?
Yeah, I do have time. I do have time. Did you have time? Yeah.
Yes.
Okay. So I'll show you some of the problems that we
Sure.
directly related to the one that you have. Okay. Thanks very much.
So what time do you want me to? So, after this, yes, I will.
Okay. Okay.